For our computational physics final project, we investigated the dynamics of a ball bouncing on a vibrating table. The height of the vibrating table will oscillate following a predetermined periodic function. The ball will be dropped from an initial height and will follow standard projectile motion. When the ball rebounds off the table, various regions of stability and chaos will emerge depending on the parameters of the simulation. This can be shown through a bifurcation diagram. In particular, we tested a sinusoidal and triangle wave with various amplitudes and frequencies to determine the effects on the interactions on the system.
This problem is similar to what we've seen in class with a ball bouncing on a flat surface. However, now we let the surface oscillate according to some periodic function. We will plot the height of the surface and the height of the ball on the same graph as a function of t. We ran all of the simulations and created all of the following plots and animations in Python. With g equals 9.81, we update the velocity of the ball at each time step via Euler's method and update the position of the ball accordingly. There's a check in the code to see if the position of the ball will be below the position of the table at the next time step. If it will be, a rebound is calculated with some specified coefficient of restitution. We'll also assume that the ball and the table are infinitely rigid, such that the collision is perfectly elastic. This process continues until the end of the simulation time.
For the sinusoidal oscillations, the velocity of the table at each point is conveniently just a cosine function, which is then added to the velocity of the ball at each collision. In the case of the triangle oscillation, we can just model the velocity as a square signal shown here. We then kept track of the peak heights of each trajectory and plotted them against various values of table oscillation frequency, and we can see emergent phenomena such as bifurcation in certain scenarios.
Let's take a look at the case of a sinusoidal table oscillation function. We can notice three main regimes. When the frequency is around 1.25, not enough energy is input back into the system to bounce the ball up, and the ball ends up hovering very close to the table. There seems to be some structure, but the dynamics are generally hard to distinguish. When the frequency is from around 1.25 to 1.7, we can see regimes of stability as well as the branching of these stable periods. Interestingly, there seem to be a few transient structures around the 1.55 to 1.6 range, which almost seem to resemble bifurcation diagrams of their own. When the frequency is above 1.7, we can see the chaotic dynamics emerge.
Here is an animation we created showing a ball bouncing in a stable regime. And now for the chaotic regime. And lastly, here is a hugging regime.
In the case of the triangular oscillation, when the frequency is below around 1.35, we notice the same hugging dynamics as in the sinusoidal case. From 1.35 onwards, there are emergent structures where the bounce heights gradually increase until dropping down once again to repeat the process. There seem to be chaotic dynamics emerging around the frequency equals 2 to 2.5 range, and then the whole structure repeats. When the frequency is too high, the numerical error from the simulation start building up and blurring the results.
Here are some animations we created for each of the regimes we just talked about.
There's a lot to expand on these simulations. From reading related literature, there seems to be a way to combine the frequency of the table oscillations and the amplitude into one parameter. As it stands right now, we have only investigated how frequency influences the dynamics of the system. Intuitively, the amplitude and frequency of the oscillations both influence energy given into the system, so they should be related in some way. Additionally, more periodic functions could be explored, something like a sawtooth wave. With more computational resources, we would also like to expand the range and increase the resolution of our bifurcation diagram to hopefully capture more structures like the transient structures shown in the sine case.
Thank you for listening to our presentation. We hope you found it at least slightly interesting and hope that you learned something new.